is for a mobile radio, it will mean something. If it is for another standard, it will mean something else, okay? Right, but this part is the same. All right, and there are a few protocols here that's part of the IP stack, and then two other protocols here which is part of the transport. Okay, so the transport has this TCP here, which is what we are interested in. Okay, all right. UDP means user datagram protocol. So UDP is a separate protocol which does not guarantee delivery. Okay, but is useful for rapid, quick transmission. So typically UDP is used for your video streaming because there's no point retransmitting the packet because it's too late already. Gone, that frame finished already. Okay, so video streaming, your iTunes, MP3 streaming, all that comes using UDP. Okay, whereas TCP will have better control in terms of the reliability of delivery of the data, and we'll see how that is being done. Okay, so on the Internet protocol side, which is this guy here, it's in the network layer, and as you can see, there are various protocols here, which we will quickly go through. Okay, so the Internet protocol, or IP, all right, provides connectionless best effort service. Okay, best effort means I try my best. If it works, it works. If it doesn't work, too bad. That's best effort. Okay, so there's no error checking because that's not the role of the network layer. There's no error checking or tracking. Okay, and the best effort uses the sequence numbers. As you saw in some of these network protocols, we have sequence numbers to make sure data packets arrive in the right order. Okay, so that's what the sequence numbers are for. So how the sequence numbers are generated is a responsibility of the upper layers. Datagrams of packets are transmitted independently and may take different routes to reach the same destination. And if you have very large packets, all right, a maximum transmission unit sizes of various sizes, you could break them up into smaller packets for transmission. That breaking up is called fragmentation, which means that the receiver side, you have to reassemble them in the right order. So fragmentation and reassembly. So those four protocols that you saw earlier here, all right, so we'll quickly describe them. The first one is ICMP, Internet Control Message Protocol. All right, it's a companion protocol to IP. So it provides mechanisms for error reporting and query to a host or router. You have query messages used to probe the status of your host or the router, and error reporting messages used by the host and the routers to report errors. So ICMP is mainly for checking on errors. The next one is IGMP, Internet Group Management Protocol. It's mainly to manage multicast groups. Multicast groups is a limited broadcast community of nodes. Okay, limited. Broadcast essentially means you set it all over the network. Broadcast. In terms of network terminology, multicast means it's a small limited set, so everyone can hear within that set. Okay, so it's used to maintain multicast group membership within a certain domain. Similar to ICMP, it has query and reply messages, which is used by the router to maintain the group membership, the multicast group membership. And then periodic messages, IGMP messages, are used to find new multicast members within the domain. And a member sends an IGMP join message to the router if he wants to join the multicast domain. Okay, and the domain is usually configured as a tree. Okay? Tree, root, branch, sub-branch, and some sub-branches, tree. Okay. The next is DHCP. You probably have heard of this. If you have a wireless router, you know as a DHCP. It gives you an address, okay, and you manage that address so that you don't need many public IP addresses. Okay, that's what DHCP does. So it's used to assign IP addresses dynamically in a domain. extension of this particular protocol called the bootstrap protocol. Usually the bootstrap protocol is encoded into the firmware of the router. Okay. Then the node requests an IP address from the DHCP server, and this protocol helps in saving IP address space. All right. So typically in your Wi-Fi router, you will have this. All right. If you recall, during the first lesson, we talked about extensions to very large Wi-Fi networks. Okay, the type you buy from the electronic shop cannot support many devices. Okay, but let's say if you put Wi-Fi into an exhibition hall where there are thousands of people, then you need extensions to the IP address space and maintaining the sessions to make it much more scalable. Okay, so DHCP is also in all your wired routers, obviously. Okay, so our 802.11, our Wi-Fi in the NUS, you have a DHCP AP to give you a address. So in terms of the intra-domain routing, we have various methods. One is the distance vector method. Distance vector essentially means that when you try to find a route in the route discovery packet will keep expanding with the address of the intermediate nodes so that you can find a path back to the source. So that's why we call it a distance vector. The other thing is OSPF. OSPF means open shortest path first, so it's based on the Jigsaw algorithm. We have already done the Jigsaw algorithm. Okay? And hosts are partitioned into autonomous systems or AS. So if you talk to network engineers, they talk about AS numbers. All right, so different organizations, they will have to procure or borrow or loan AS numbers so that they can be used in their routers, and then their IP addresses and all that will be known to the internet. Okay. So hosts are partitioned into autonomous systems or AS, and AS is further partitioned into OSPF areas that helps border routers to identify every single node in the area. Okay, so some organizations may have more than one AS number depending on how they partition their internal network. Then link state advertisements are sent to all routers within the same hierarchical area. So the link state advertisements are used to manage the traffic flows within that area. Finally, you have the BGP. BGP is where you do the peering across different AS subnets. Okay. So the intra-autonomous systems communicate with each other using path vector routing protocol. So every time you see a vector, it means it adds more addresses. Okay. So that's the IP part. So essentially it does with networking, finding the destination from one place to another, okay, from the source to the destination. So now we come to the TCP part, okay, transmission control protocol. So it's a connection-oriented transport protocol. What do you mean by connection-oriented? In other words, it establishes a virtual connection from A to B, and whenever you send traffic, it will always take that path. Okay, so that's called a virtual connection. So it's a connection-oriented transport protocol. So TCP aims to guarantee end-to-end ordered delivery of data packets over wired networks. So it was originally designed for wired networks in the days of ARPANET. Okay, so that's back in the 1970s, 70s, so 40 years. So the basic functions include flow control, error control, and congestion control. Those are the basic functions. Flow control, quick recap, means I'm the sender and you are the receiver, and you can only receive at a certain rate. If I give you too fast, what will happen? overflow of your input buffers, right? Data will be lost. So flow control means that we have to have a handshaking such that you can say, stop, wait, let me clear my buffer first. Clear already, you can continue. That's flow control. Okay, flow control. Error control is obvious. If you have errors, then it has to be retransmitted. Okay, and we'll see some methods of error control afterwards. Okay, and congestion control will be helpful to the network side. Okay, so if certain nodes are congested, they're dealing with too much traffic, then you divert the traffic to another part of the network. Okay. So in TCP, to carry out all this, particularly the error control part, it uses sliding window protocol. Okay, we will explain what that means afterwards. All right. So the sliding window protocol is to implement the flow control. Okay. So there are three windows: a congestion window, a advertised window, and a transmission window. Okay, so the congestion window is determined at the source. Okay, it indicates the maximum number of segments of packets a sender can transmit without congesting the network. Okay, repeat now. Maximum number of segments a sender can transmit without congesting the network. So this number is determined by the sender based on feedback from the network. So the sender has a congestion window that is determined based on information of the network. The next window is the advertised window. This is at the receiver side. So it's specified by the receiver, the destination, in the acknowledgements. So the advertised window indicates to the sender the amount of data the receiver is ready to receive in the future. This is the amount that I can take. Don't give me more than that. That's the advertised window. Finally, the transmission window is what is actually used to manage the packet flow. Okay? It determines the maximum number of segments that the sender can transmit at one time. That means maximum number of packets it can transmit at one time without receiving an acknowledgement from the receiver. Now the most basic is I send you one, you acknowledge. I send you another one, you acknowledge. That's the most basic one. But now we're saying I can send you n number of packets, then you acknowledge. Okay, so the acknowledgements is based on this sliding window. That's what the window is. But this window is dynamic, depending on the advertised window and the congestion window. And you take the lower of those two. All right? So to avoid network congestion, and receiver buffer overflow, the size of the transmission window is determined as the minimum of the congestion window and the advertised window. So this is play safe. Minimum of the two. All right? So these are the basic functionalities of the TCP. Is to notify the sender that data is correctly received. So TCP employs a cumulative acknowledgement mechanism. So you send me n, I will tell you, okay, I got n. I don't have to tell you each time I receive one. So it's a cumulative. Upon the receipt of an acknowledgement, the sender knows that all previously transmitted data segments with a sequence number less than the one indicated in the acknowledgement are correctly received at the receiver. We'll show you some flow diagrams afterwards. Okay? So you send me 5 packets, all right? So now I'll tell you, okay, I've got your 5 packets, all right? And inside there, the packets have a sequence number, all right? So all this will be known. In the event, in the case of an out of order segment, how do you identify that? Based on the sequence number. So if it's out of order, all right, a duplicate acknowledgement is generated and sent back to the sender. Okay, when you send a duplicate, and I'll explain what is duplicate when you see the flow diagram. A duplicate, whenever the the sender receives a duplicate packet, he knows something is wrong already. Alright? So let's take example now. You are sender 1, sender 2, sender 3. I'm the receiver. Okay? So, no, sorry. You are one sender, but you are packet 1, packet 2, packet 3. Same, okay? So packet 1 comes. Packet 2 you send. Packet 3 you send. Okay? So if my window is 3, I will then reply and say, I got all 3 packets with these sequence numbers. So the sender will know that this was successfully received. Okay? But let's say it comes in such a way that the order was wrong, the sequence number was wrong for whatever reason. Alright? So when I send back to the sender, I say, okay, I got 1, 2, and 3, thank you. Okay? Actually, I don't say 1, 2, 3. I say, I just got 3. It means that by default, I already got 1 and 2. Okay? Right. Then, if anything goes wrong, I will resend acknowledgement 3. That means there's a duplicate acknowledgement packet. Okay? Alright, that's what we mean by duplicate. Now, in the case of a wireline network, a wired network, okay, if you have an out of order delivery, usually that implies a packet loss. Usually, okay? If 3 duplicate cumulative acknowledgements are received, the sender will assume that the packet is lost. So this is the traditional TCP. Now the packet loss is also assumed if the sender does not receive an acknowledgement for the packets within a certain timeout interval called the retransmission time, or RTO. So I'm a sender, I send something to the destination, the receiver, I start my RTO timer. If I don't hear an acknowledgement when the RTO timer times out, I know that I have not been successful. And I will have to retry again. Okay? Now the RTO time out is usually dependent on the estimated round trip time, RTT. Round trip time is have you heard of the word ping? If I ping a particular node, the time it takes to go there and come back is called the RTT time. Alright? Okay? So if you are in shell mode, command line mode, you do a ping and you put in the IP address, if you know the IP address. It will give you a script that shows you what is the time it took to do the RTT. Okay, have you tried that, some of you? Have you tried it? Yeah. Okay? Yeah, you try it, so you know what I mean by RTT. Okay? So, for small or medium-sized area coverage, it's not a problem. But for very far distances, you have a problem. Okay? You have a problem. For example, if you are trying to reach a server from here in Singapore trying to send data to another server, say in the US, okay, West Coast, Pacific side, all right, it will probably take a trans-Pacific route, depending on how you do it, okay, trans-Pacific route, all right, and the RTT will be of the order, of about 200 milliseconds. 200 milliseconds of that order. Okay? Yeah. So by retransmitting the lost packet, TCP achieves the reliable data delivery. Okay, so what are the challenges when it comes to the wireless channel? So don't forget, TCP/IP was designed for wired. Wired is supposed to have very consistent network quality. Okay? So the challenges that we face in a wireless environment, well, of course, the channel errors. That's the number one. Okay, in a wireless network, you have high data error rate. Okay, because of fading, because of shadowing, whatever nonsense you have in the channel. Okay, so this will lead to losses of the packet or corruption of the packet. Okay, so the data errors could be at the data packet that you send out. The errors could be in the acknowledgement that you're also trying to send out by the sender. Either way. Okay. So if a sender cannot receive an acknowledgement within the RTO timeout, okay, the TCP sender immediately reduces the congestion window to 1 second, that means only one packet. Okay, and exponentially backs off its RTO and retransmits the lost packet when the backoff time expires. Right? So if your congestion window is reduced, then this time you're back to a situation where you only can send one packet at a time. Okay? Right. Then the channel errors also may cause congestion, the congestion window size at the sender to remain small as a result of that. So you don't have the advantage of sending a whole bunch of packets and then expect an acknowledgement back. So you're basically a sliding window protocol breaks down. Okay, breaks down. The second problem is mobility. When nodes travel, right, around, you have the handoff from one place to another place. You have the handoff. So normally the handoff will cause temporary disruptions, and that could lead to packet loss. So TCP will suffer a lot if it treats such losses as congestion, because it's not congestion, it's packet loss. And invokes unnecessary congestion control. Congestion control means that they will start shrinking the congestion window at the sender side. And the handoffs are expected to be more frequent in next generation cellular systems. Okay? Because your cells are getting smaller and smaller. Alright, whether there's a radio station. You can see you can tell that there is a mobile RF front end that looks like a bit like a cone. It looks a bit like a cone, something like this. So looking upside down. You see on the roof below is an RF. Okay. The antenna for the mobile radio base station. Okay, for in-building. So handoff will be a problem and will get more and more frequent. So TCP will need to find ways to handle this. Traditional TCP doesn't do this very well. You have similar problems with wireless LANs as mobile users or pedestrians. You walk from one place to another. The link breaks, okay? So the next thing is asymmetry. Sorry, no set of notes. I think you're looking at the wrong one. This is the whole set. It cannot be so fast. So I might have to skip a couple of slides. That's why I didn't explain all this. Okay, so as I mentioned earlier, all right, we have this flow control. So that's why I should have explained all this. All right, so this is called automatic request, automatic repeat request, ARQ. So it's used for error control and flow control. So we're going to go through some of these methods. Selective repeat is the same as selective acknowledgement, same thing. Huh? So The first and simplest is of course this one. Okay, so you stop and wait. Basically, I send you something, you acknowledge. I send you something, you acknowledge. Okay, and there's always a timeout period. So if you don't get a timeout period, you assume you have not been successful and you have to resend again. Okay, so this is the basic one. It's the simplest ARQ protocol, all right? And capacity is limited to 2 times the round trip time. Okay, we saw this capacity limit earlier in the example of Aloha, remember? Okay. So this is a stop. So these are, for example, you got this packet, but your acknowledgement did not get through. So this is called act loss. You send something, but the thing did not get through. So this is a packet loss. Then if your timeout period is too short, you send something, this guy came back later, but you time out already, and then you resend. If your timeout period is too short. So your timeout period should not be too short. Okay, that's why a lot of this had to take notice of the RTT. Okay, RTT. Okay, round trip time. Of course, if you have a good network, you can fill the pipeline. And then the other one come back on. Or the acknowledgement back. That's called filling the pipeline. Send multiple packets without waiting for the first to be acknowledged. Alright, and the number of packets in flight will be the window size, whatever the window size is. So, reliable unordered delivery, several stops and waits, send new packet after each act, and so on. Sender keeps list of unact and is not yet received or negative acts, packets, and then resends after a timeout. Receiver, same as stop and wait. How large a window will depend on quality of the line and RTT. Those are the two things. Okay, if the quality of the line is good and your RTT is short, you can have a larger window. But if your quality of the line is bad and your transmission delay, which determines your RTT, is long, then you have a shorter window. So the shorter the window means, of course, it will affect the throughput. Okay, the TCP throughput. So, oops. Okay, next is the concept of sliding windows. Okay, so in the sliding window, the sender can send multiple packets within the window. The receiver can receive packets within the window and holds on to a packet until all prior packets have arrived, and both sender and receiver work within buffer capabilities. Okay, so actually I jumped the gun just now because that was the whole set of loads. So now you know why I'm putting all this in now. This was a revise so that you know the context of where all this came from. Okay? And it's common to use a circular buffer. Do you know what's a circular buffer? Anyone? You know what is a normal buffer? It's linear. Okay? So a normal buffer will be like a first in, first out queue. That's a common one. Alright? A circular buffer is think of a buffer that is circular, and you have a read pointer and a write pointer. Alright? So these 2 pointers keep moving. So if you read already, then move to the next one. Read next one, read next one. Similarly, you write, then after that the next one, go to the next one. So what happens is like a rotating first in, first out. That's called a circular buffer. Okay? So it's quite common to use that. Alright, then the packets in transit should be less than the buffer size, less than or equal to the buffer size, and only move forward when the sender and receiver agree packets at the beginning have been received. Okay, right. So we're going to look at 2 loss recovery mechanisms. The first one is called the go back end. There was some error in your notes. The diagram, I checked it, it's not there. So in this scenario, you have the sender on the left you have the receiver on the right. Okay, so this is what happens. So sender sends out packet 0, it takes some time to get to the receiver. Receiver is successful, he sends X0. Okay, X0. Meanwhile, sender sends packet 1, successful, receiver sends acknowledgement 1. Okay? Next, sender sends packet 2. So this example is go back 2. Okay? Go back 2. Okay? Actually, go back 3 because I'm sending the third one now. Go back 3 because I'm starting from 0. So go back 3. So he sent packet 2. He received packet 2 and sends out Act 2. But Act 2 got lost. Got lost. Okay? So your picture is actually missing some details. Got lost. Now, then he sends out packet 3. Now, because the receiver was not successful here, and then this guy keeps sending here over here, he will discard and do a duplicate act of Act 1. Okay, duplicate of Act 1. Then maybe sometime later, this Act 0 came back, so he resumed sending packet 4. But he will discard because you know why? He said, hey, what happened? Huh? Shouldn't I be getting packet 3 now? Why is there packet 4? Alright, so there is some problem here. So he keeps sending out Act 1, Act 1, Act 1. Alright? So later the packet 2 timeout, sender never got Act 2. So now he has to send packet 2, packet 3, packet 4, packet 5 again. So this is go back end. Alright? There are variations of this as well. I'm just taking one particular version of go back end. There's another version of go back end where it uses NAK, non-ACK. Alright? If you look at examples, just go Google, go back end ARQ. There are many videos that you can find. Alright? Go back, /back/n space ARQ. Just go Google and you can find. Okay? So this is one of those examples inside. Now the other one is called selective act or selective repeat. Okay, and I have a couple of slides for this. So the receiver individually acknowledges or correctly received packets, buffers packets for eventual in-order delivery to upper layer to give it to upstairs. Alright. Sender only resends packet for which act not received. Alright, and sender timer for each unact packet. There's a timer, and there's a sender window, n consecutive sequence numbers, limit sequence numbers of sent and unact packets. The advantage is it reduces number of resends. The disadvantage is increased complexity. Now notice the now drop n, go back n, because the packet 2 was not successful and you had previously sent out 3 and 4 as well. Now he has to resend 2, 3 and 4. In selective, if 2 didn't go, only 2 needs to be resent. 3 and 4, if we got the acknowledgement later, no problem. Okay? Right? So the sequence is over here. You don't have this slide. I will upload this fresh set of notes later. Okay, you don't have this slide. So step 1, okay, or the other way around. Sender is on the right, receiver is on the left. Okay, we call this guy the client. This is the client, this is the server. Client is asking for data. So segment 1 is sent. Okay, then segment 2 is sent, but it didn't make it. So segment 2 is lost. Okay, segment 2. Right? Then this guy is still sending segment 3. Right? Later when this segment it acknowledges back here. Segment, okay, so let me read this one. Step 2. Client realizes missing segment between segments 1 and 3, because he's a client. He saw 1, he saw 3, but this one was not there. Okay? Sends a duplicate act for segment 1, which is this guy here, a duplicate act for segment 1 here. Alright? At the same time, it also has this selective act option to show that it has received segments, alright? Also include the SAC, okay, indicating that it had received segment 3, because if you look here, he received segment 3. Okay, so he sends this act plus this sec3. Then the next step is step number 3. Client receives segment 4, so he receives segment 4, and sends another duplicate act for segment 1, but this time expands the SACK or selective act to show that it has received segments 3 and 4. You can see segments 3 and 4. Okay? Then step 4 is over here. Server receives client's duplicate act, which is this guy here. You receive client duplicate act for segments 1 and sec for segment 3, as you can see here. Act 1, sec 3. From this, server deduces that the client is missing segment 2. So segment 2 is retransmitted. So this segment 2 is retransmitted. Next sec received by server indicates that the client has also received segment 4, as you can see from here. Sec says I got 3 and 4. So no more segments need to be retransmitted, only segment 2 needs to be retransmitted. And then at step 5, client receives segment 2 and sends act to indicate that receipt of all data up to and including segment 4. Okay, so in selective act, you only need to resend the missing one. In go back one, you resend the missing one plus all the ones up to the timeout. Okay, so that's a big difference. Question? Okay? Alright, so that was what I should have covered first before I go into this. This is you heard already. Okay, you heard all this already. So we got all this done. Okay, so now you see that because of the poor channel quality in the wireless environment, obviously TCP/IP will not work very well. Okay, the throughput will be so bad. All right, because things keep breaking down. So we look at two examples of how we can overcome this problem. Okay, the first example is indirect TCP. It is a split connection solution. The second example is Snoop, which is a proxy-based solution. Okay, so let's look at indirect TCP first. So we have the fixed host of FH on the left. This is our fixed host. A fixed host wants to send something to the mobile host or vice versa. Okay, so the connection is split into two parts. The wired part, which is the TCP connection 1, between the fixed host and the base station, okay, and TCP connection 2 between the mobile host and the base station. So it's a split solution. Okay, so this is what happens. So in the indirect TCP, it's a split connection solution, as you saw in the diagram just now, between the mobile host and the base station. Over the wireless medium is one connection, and then between the base station and the fixed host on the wired line is the other connection. Okay. Now packet is sent, which is sent to the mobile host, is first received by the base station, as you can see here. First received by base station over here. Okay. The base station then acknowledges to the fixed host and then forwards the packet to the mobile host. All right? Now, what does that mean? It means as far as the fixed host is concerned, it has been successfully delivered. It doesn't know about the wireless part, because the base station already told the sender, hey, no problem, acknowledge. Okay? Now, if the mobile host, so between the base station and mobile host, then they might use a lightweight protocol so as to get it across, okay, which is described in the next slide. So if the mobile host moves to a different cell, okay, while communicating with a fixed host, the whole connection information maintained by the current base station has to be transferred to the new base station. Otherwise, you cannot do the handover, right? All of that has to be transferred. Now, the fixed host is unaware of all these things happening because the base station already acknowledged. Okay? So the fixed host is unaware of this redirection and is not affected when this switch occurs. However, you see, the end-to-end connection is split. The TCP connection over the wireless link can use some wireless link-aware TCP, which need not be the same as the traditional TCP, okay, link-aware, which may be tailored to handle wireless channel errors and handoff disruptions. So, what does that mean? Indirect TCP separates the congestion control functionality on the wireless link from that of the wired, which enables the two kinds of links to identify different reasons for packet losses and then take corresponding action. Okay. Now, since the TCP connection is broken into two, it is possible for the mobile host to use some lightweight transport protocol instead of the full TCP IP to communicate with the base. All right. This feature is desirable, so now you tune it such that you deal with the poor wireless channel. Okay. So this feature is desirable since the mobile host has limited battery and limited processing power. However, indirect TCP violates the end-to-end semantics. That means the end-to-end principles, if you like, of the TCP acknowledgement, as both the wireline part and the wireless part of a connection have their own acknowledgement mechanisms. Okay? So control overhead is of course considerable, especially when you have to pass information from one base station to another. Right? So that's the indirect TCP. Any questions?
Is this currently used? Is it currently used in our mobile system?
Currently?
Used in our mobile system.
A variation of this. Okay, these are very early proposals, but it's easy to understand.
No illustration.
Yeah, there of course a solution, otherwise your mobile phone won't work. you watch YouTube and then keep breaking, right? Okay, so it's from all this earlier work that a more robust standard is put in place for your 3G, 4G, and so on. Okay, not 2G. GSM cannot stream things, it's too slow. Okay, 3G and 4G can. Okay, the second method is called Snoop. Okay, so this one is a proxy-based solution. Right? So it improves on TCP by modifying the network layer software at the base station. All right? And preserves the end-to-end TCP connection. So it preserves that. So, excuse me. It adds a snooping module to the network layer, which monitors every packet that passes the base station in either way, either direction. So if the TCP packets are sent from the mobile host from the fixed host to the mobile host, the Snoop module will cache each packet that has not yet been acknowledged by the mobile host. Meanwhile, Snoop module keeps track of all acknowledgements from the mobile host. Then the Snoop module deems a packet loss occurred if it receives duplicate acknowledgement or its local timeout expires. Okay? So in this case, the lost packet is retransmitted by the mobile host if it has been cached. Okay? So a duplicate acknowledgements, if any, are suppressed. Okay? Unnecessary congestion control mechanisms invocations are avoided since packet losses due to wireless channels are hidden from the fixed host. Okay, so let me summarize this. Okay, I have the fixed host here, I have the base station here, and I have my mobile here. Okay, right? So I'm trying to send data from here to here. So I send it through the base station caches the data. Alright? Base station will then send it to this guy. If everything goes well, it will receive an acknowledgement. If it doesn't go well, it has to try again. Okay? Until he gets the acknowledgement, then he will send the acknowledgement. So he acting as a proxy now. Got it? Now you can think of the other way the same thing. He wants to send to him. So you cache it, right? But usually this thing no problem, because it's wired. Okay, especially this one is successful enough. Okay, so it's slightly different. So that's the next slide. When packets are transmitted from the mobile host to the fixed host, mobile host cannot tell whether a packet loss is due to errors here or due to congestion and errors here. Okay. Hence, the TCP selective acknowledgement option is used, which we just covered just now. Okay. Why? Because it's more efficient. You only resend what was lost. You don't resend what was lost and all the things after that. Okay. So the selective acknowledgement enables sender can retransmit multiple lost packets in one RTT instead of detecting only one lost packet, because this is a short distance. Short distance. Okay. At the base station, when the Snoop module notices a gap in inbound sequence numbers of packets from here, so there's a gap, selective acknowledgements are sent to this. So selective acknowledgements is applied here between the mobile and the base station. Okay. Upon receiving selective acknowledgement, mobile host will retransmit the lost packet for local loss recovery. Okay. So Snoop is also designed to take care of handoffs. So how does it do that? Several base stations near the mobile host, maybe there's another base station here, another base station here. Okay. Several base stations near the mobile host form a multicast group, okay, and buffer some latest packets from FH, from the host. Okay. Prior to handoff, MH will send out a control message to determine which base station with the strongest signal should be the one forwarding the packet to the mobile host. Okay. And all other base stations just buffer the packet. Therefore, both handoff delay and packet loss is reduced. So if this connection is too weak and you've got to hand off to someone here, for example, let's say it's moving this direction, they are part of the same multicast group. So the packets that was meant to be forwarded is also here in the same multicast group. So it's very fast and very easy for this guy to take over from that guy, because they're part of the same multicast group. Okay? So Snoop improves TCP performance by performing local retransmissions across the wireless link without affecting end-to-end semantics. So it it focuses on this part between the base station and the mobile home. Although TCP performance during handoffs may be improved, considerable overhead is incurred for maintaining the multicast base station group and state transfer from one base station to another. Okay, you do need to have special care to handle interactions of the Snoop module retransmission and TCP end-to-end retransmission, because Snoop is similar to link-level approaches over wireless links, okay, because of the state information that is being kept across the multicast group. So that is a brief summary of Snoop. All right. So what that means is that the basic TCP/IP protocol will not work well in a wireless environment because of all these challenges. And so additional things needs to be done. All right. And lightweight protocols allow it to happen at the wireless link. Selective acknowledgement can be used so that it is more efficient in the retransmission. Okay, selective. Okay, so there are other TCP enhancements. These are examples. I'm not going to go through it. All right, TCP SAC, WTCP, freeze TCP, explicit band state, etc., etc. Okay, and then for fast retransmission approaches has also been considered. Tries to reduce the effect of handoff, reduce the effect of having too many duplicate acknowledgements, avoids cost, timeouts at the sender, and then to speed up the retransmission. Another one is called TULIP. So all these, you put in, go to Google or Google Scholar, you can pull out all the papers. Here are some of the references. Any questions?
Basically, the concept is send something, fail, send again.
Yes, but the question is, how often do you need to do it, and how efficiently can you do it? Okay, and that depends on how bad is the channel. Okay, so the big difference between a wired and a wireless channel forces you to come up with more innovative ways to deal with the poor channel quality. Okay. But poor channel quality also happens in wired networks. Okay, I'll give you an example. So I mentioned the thing about, say, transmitting large volumes of data between here, say, and the US. Right? Now that you know what TCP/IP is about, you have your congestion window at the sender side, you have your advertised window at the receiver side, and dynamically you determine what is the transmission window based on the minimum of those two. Correct? That is how it works. Now that works okay if your RTT is small. If your RTT is large, like intercontinental distances, right, you cannot have super large windows. What happens if something goes wrong? So TCP/IP actually fails when you want to do large data transfers over long distances, over networks that are long distances. So you may have a 10G line, 10 gigabits per second line, 10G, or 100G line from Singapore to Los Angeles. But if you use traditional TCP/IP and you tune it, at best you can get is 30 megabits per second. 30 to 40 megabits per second. All right, so there's been quite a lot of work that has been done by various groups across the world. All right, across the world to deal with this problem. So this problem has a name. It's called the long fat pipe problem. Long fat pipe. Why long fat pipe? Obviously the pipe is wrong, right? It's fat because you got all the bandwidth in the world, but you cannot use it. That's the problem. So I work quite closely with the group at the National Supercomputing Center and various other communities, and we demonstrated methods over the last couple of years where we can actually increase the throughput to almost 98% of the pipe. Okay, 99%. Okay, and the common approach for doing that is to use multiple TCP streams. Okay, number one. Secondly is to use what we call jumbo frames, large Ethernet frames. Okay, what's a jumbo frame? Typically will be of the order of thousands or tens of thousands of bytes. Okay, all right. And then you have to tune those three windows. Okay, so in fact, right now we have a competition going on. We call it the Data Mover Challenge. Okay, to see who can come up with the best method to transfer data in the shortest time over the following sites: Singapore, US, Japan, Australia. Singapore being the center.
What's the record?
Huh?
What's the top record right now?
Haven't finished yet. We're in the middle of the competition. So there was something like 14 or 15 groups globally who wanted to participate, but we shortlisted it down to 7. So we're only up to halfway right now. Halfway, okay? So I can't really say who is the best yet because we're only halfway. Okay? Each group is given 1 week to set up their system. So we basically set up servers in these 4 places. All right, we gave them a heterogeneous data set of 2 terabytes. Okay, heterogeneous meaning of different sizes. Some files are smaller, then you have gigabyte files, heterogeneous. All right, and they're supposed to transfer all this either memory to memory or disk to disk. Okay, both, not even and. All right, obviously memory to memory is much faster. Disk to disk is much slower because disk to disk depends on your disk I/O. How fast you can read and write. Okay, so that slows things down. Okay, so that's the competition that's going on. Right, so indeed this is the problem when you have large distances. Okay, the long fat one. Okay, so the competition is configured in such a way that you need to you do it over the traditional network. All right. I don't know if I told you this. I told you that I have a IoT test bed, right? But have I shown you what it is?